Welcome viewers. We know that Gauss's law states that the net amount of electric flux passing through a surface is equal to 1 by epsilon naught times the charge enclosed by the surface. This law relates the electric field at any point with the net amount of charge enclosed by the surface. Further, this law can be applied to find electric field due to uniform and symmetric charge distribution. In this program, we will try to find electric field due to a uniformly charged thin spherical shell. Let us consider a uniformly charged thin spherical shell having uniform surface charge density sigma. Let us suppose this O is the center of the cell and capital R is the radius of this cell, and we wish to find electric field at any point which may lie outside the cell, on the surface of the cell or inside the cell. Can you guess the symmetry for electric field at any point around this cell? The situation has obviously spherical symmetry. The field at any point P outside or inside can depend only on the distance of the point from the center. You may call it small r. That is the radial distance from the center of the cell to the point, and it must be radial, that is along the radius vector. So, let us find electric field at any point outside the cell first, outside the cell. Suppose we have a point P and this point P is lying outside the cell at a distance small r from the center of the cell. So, let us imagine a Gaussian surface in the form of a sphere of radius small r. Now, let us cut a small area element delta S from the Gaussian surface around this point P. Suppose the area of this small element is delta S, and you know that the direction of area element is always in the direction of outward normal. So, this will be the direction of area element. You can call it ds vector. By spherical symmetry, we can easily observe that for all points on the Gaussian surface, angle between electric field and normal is always 0. If we look at electric field at this point, due to this charged spherical shell, it should also be radially outward. Now, flux through the area element delta S, you can call it delta phi, it should be E dot delta S, and we can write it at mod E mod delta S cos 0, as the angle between electric field and area element is always 0 throughout the Gaussian surface. So, the small flux passing through this small area element delta S will be E delta S. Let us give it equation number 1. Now, summing over all such area elements which can be cut from the Gaussian surface, we get total flux phi, which is equal to sum of the flux of all such area elements, summing over all area elements delta S. So, we can write E delta S, and by symmetry we can observe that E is constant throughout the Gaussian surface. So, we can take it out of the summation sign and it becomes E multiplied by summation of delta S over all area elements, and the sum of all the area elements that can be cut from the whole Gaussian surface will give us what? It will give us the total area of the Gaussian surface, which is a sphere of radius small r, and we know that the area of a sphere is 4 pi small r square. We can give it equation number 2. So, it is the total flux passing through the Gaussian surface. Now, from Gauss's law, we know that electric flux through a closed surface S is equal to the amount of charge enclosed divided by epsilon naught. From Gauss's law, total flux passing through a surface is equal to amount of charge enclosed Q enclosed divided by epsilon naught. And here, what is the charge enclosed? It is the charge which is enclosed, which is distributed uniformly over the surface of the sphere of radius capital R. And you can find this charge just by multiplying the charge density with the area of the sphere. So, now we can write the amount of charge enclosed is sigma multiplied by the area of the sphere of radius capital R, 4 pi r square. So, the total flux passing through this Gaussian surface with the help of Gauss's law can be written as, by putting the value of this charge enclosed in this formula, sigma multiplied by 4 pi r square divided by epsilon naught. We can give it equation number 3. So, we have found out electric flux using the general formula of flux by summing over the flux of all the area elements which has been cut from this Gaussian surface, which was E into 4 pi small r square according to equation number 2, and now we have found out electric flux using Gauss's law. Now, from equation 2 and equation number 3, by equating them from equation 2 and equation number 3, we can write E into 4 pi small r square is equal to is equal to sigma into 4 pi capital R square divided by epsilon naught. From here we get electric field at point P is equal to sigma into 4 pi capital R square divided by 4 pi small r square epsilon naught. So we get sigma into 4 pi r square is q, and it is, by reshuffling it, you can write 4 pi epsilon naught multiplied by r square. So this is the magnitude of electric field at any point P which is lying outside the uniformly charged spherical cell. So this is the magnitude part. Now vectorially you can write it as in vector form electric field at any point outside, you can write it E outside. Suppose this is the electric field at any point which is lying outside the cell. So it will be 4 pi 1 by 4 pi epsilon naught q by r square multiplied by r cap, because the charge on the surface of this cell is positive. So electric field will be radially outward. If the charge on the surface of the cell would have been negative, then this electric field would have been directed radially inward. Now this r cap is a unit vector normal to the thin spherical cell which is directed radially outward. So this is the final formula for electric field at any point P which is lying outside the cell. Now have you ever seen this formula earlier? Think over it. Yes, you are thinking in the right direction. It is the formula of electric field due to a point charge q at a distance r from it. Suppose this is a point charge q and we wish to find electric field at any point which is situated at a distance small r from it, then the formula for electric field at this point is the same. Thus, for all the points outside the cell, the field due to a uniformly charged cell is as if the entire charge of the cell is situated or concentrated at its center. Now let us find electric field at any point on the surface of the cell. If this point P lies on the surface of this cell, then the distance small r from the center to point P, this distance becomes equal to the radius of the cell. That means you can write small r is equal to capital R for all the points which are lying on the surface of this cell. Now if we replace small r in this formula with capital R, then the value of electric field at any point on the surface of this cell, you can denote it by E surface, and it is equal to 1 by 4 pi epsilon naught q by capital R square, and again it is directed radially outward. If the charge on the surface of the cell is positive, that means q is greater than 0, and it is directed radially inward if the charge on the surface of the cell is negative. Now, let us find electric field at any point P which is lying inside the cell. Suppose this is our cell which is uniformly charged, having surface charge density sigma. This is the center of the cell and its radius is capital R. Again, suppose we wish to find electric field at any point P here, and this point P is lying inside the cell. Again, let us draw a Gaussian surface, and by spherical symmetry the shape of the Gaussian surface is again spherical. So, it is a sphere of radius small r. Suppose the distance of the point P from the center is small r. Now, let us cut small area element delta S from the Gaussian surface, and the flux. So, we are finding electric field at any point inside the cell, inside the cell. So, flux through this small area element delta S, it is delta phi, and it will be again E multiplied by delta S. And because electric field is radially outward, so angle between electric field and area normal is always 0 degree. So, cos 0 is 1, so delta phi will be E delta S. Now, summing over all such area elements, the total electric flux passing through the surface can be written as summation delta phi. So, and again because E is constant, so we take it out of summation sign and it becomes E sigma delta S over all delta S, and total electric flux passing through the surface becomes E multiplied by 4 pi small r square. Let us suppose it is equation number 2 and this was equation number 1. Now, using Gauss's law, from Gauss's law we know that electric flux passing through a surface is equal to amount of charge enclosed, you can call it Q enclosed, divided by epsilon naught. Can you tell what is the charge enclosed by this Gaussian surface in this problem here? Yes, you are thinking in the right direction. The amount of charge enclosed by this Gaussian surface is 0, because the whole charge is distributed on the surface of the cell. So, amount of charge enclosed is 0. So, the flux passing through this Gaussian surface is 0. Let it is equation number 3. Now, from equation 2 and 3 we can write from 2 and 3 E into 4 pi r square is equal to 0. This implies E is equal to 0. Hence, electric field at any point P which lies inside the cell is 0. Now, let us draw the graph showing the variation of this electric field with distance of the point from the center of the cell. Before drawing the graph, let us summarize the results electric field at any point outside is 1 by 4 pi epsilon naught q by r square multiplied by r cap. Electric field at any point on the surface, it becomes 1 by 4 pi epsilon naught q by capital R square multiplied by r cap, and electric field at any point inside the cell is 0. So, these are the final results that we have obtained, and on the basis of these results we can easily draw the graph showing the variation of electric field with distance of the point from the center of the cell. Can you try it? So, we can take electric field on y axis and the distance of the point from the center of the cell on x axis. If we look at electric field at any point outside, it is inversely proportional to r square, and electric field on the surface of the cell is constant. As you know that 1 by 4 pi epsilon naught is constant, charge is constant, and the radius of sphere is also constant, and electric field inside the cell is 0. That is, starting from the center of the cell up to the surface of this cell, for all points which are lying within the cell, electric field is 0. So, from 0 to capital R, 0 to capital R, electric field is 0, it is 0, and as soon as we reaches the surface of this cell, electric field instantly grows up to this value. Suddenly, the electric field on the surface acquires this value, and after that, when we go outside the cell, electric field varies inversely as the square of distance of the point from the center of the cell. So, graph will go like this as rectangular hyperbola. For outside, electric field is inversely proportional to r square, and this point gives the value of electric field which is on the surface of the cell. Keep watching our videos to enjoy learning physics. Happy learning.